We were considering heat utilization in furnaces, and in the previous lecture to this, we were discussing role of heat recovery and efficiencies, and there I have taken two cases. One case was 110% excess air and no air leakage, and case 2 was 110% and 15% air leakage, and there we have found that air leakage is detrimental to the operation of the furnace as well as to the fuel consumption. And through the illustration, it was possible to illustrate the increase in fuel consumption due to air leakage. Now, physically you can think whatever amount of air that is leaked into the furnace, that particular amount of air will not be passing through the heat exchanger or a regenerator, and it is obvious because you are working with the total amount of air. You are keeping total amount of air constant. So, whatever air which is leaked, that will not be passing through the regenerator, and hence that much amount of air will not be preheated, and accordingly less sensible heat will be input into the furnace, and obvious this will lead to increase in fuel consumption. Now, let me take another case, say case 3 if I take, and case 3 concerns, say now I am using 125% excess air, 125% excess air, and air leakage is 15% of theoretical air, this is the air leakage. So, air leakage is 15% of theoretical air, and we are retaining relative efficiency of regenerator. We are retaining relative efficiency of regenerator, that is around 80%. Now, here I must tell you something. Now, since we have increased the amount of air, so we have increased the amount of air than the previous case. Previously it was 110%. Now we increase to 125%. As a result of increase in excess amount of air, there will be increase in the volume of the products of combustion, and as such the heat exchanger, which is of same cross section as it was in the previous case, so products of combustion will be moving faster than case 1, because here the more volume of the product, cross section area is the same, so velocity will be higher. So, it is quite possible that the relative efficiency will be somewhat lower than what we have assumed here, 80%, but well, for the sake of comparison we are not touching the relative efficiency, we are keeping same as it was in case 1 and case 2 equal to 80%. But this point is to be remembered, because heat exchange occurs between the flue gas and air. So, accordingly the residence time is important. In spite of that, for comparison purposes we are keeping relative efficiency to be same. Now, so again we have to calculate afresh the amount of air and amount of POC. So, now if we calculate, say total air required, that will be equal to now 0.595 kg moles. Now, air through the regenerator, air through regenerator, that will be equal to 0.5236 kg mole. So, now we know, now mind you here the composition of the fuel is same as in case 1 and case 2, and just for repetition I write down the composition of fuel is 90% carbon and 10% hydrogen as it was in the previous case. So, now if I wish to represent the material balance of this particular furnace which is equipped with the regenerator, then I have to calculate also the flue gas. So, the composition of flue gas, or you can also call POC. Now, this composition will consist of CO2 and this will be equal to 0.075 kg moles. Now, remember, by taking excess air, the amount of CO2 is not going to change. Similarly, that of H2O, that will be equal to 0.050 kg mole. Amount of nitrogen, that will be equal to 0.47 kg mole, and amount of oxygen, that will be equal to 0.025 kg mole. So, the total amount of POC, that is equal to 0.62 kg mole, or if you want to know the percent in percent, say CO2 12.1, 8.1, 75.8 and 4.0. Obviously, with the increase in air, the percent CO2, H2O, N2, NO2 will be different than what they were in case 1 and case 2. Now, we can represent this on a material balance diagram, which is as follows. So, I just represent it by a box, which is normal when you want to represent the material balance. So, this is a furnace which is same as it was earlier. Now, this is the POC or flue gas, whatever you would like to call. This is entering into a preheater, or this you can also call as a regenerator or a recuperator. This preheater, it could be, or it is simple and heat exchanger. So, this preheater could be anything. Now, here flue gas exit. Now, from here air will enter, and this is the preheated air. Now, total air in furnace, total air that is required for combustion, that is equal to 0.595 as I wrote down earlier. So, here air leakage is 15% of theoretical, you have to calculate the theoretical amount. So, the air leakage now, as I wrote earlier, that is 0.0714 kg mole. This is the air leakage, and the air which is used for preheating, that will be 0.5236 kg mole, and this amount of air, the preheated air, and its amount will be how much? 0.5236 kg mole. That will be the material balance. Now, here for the sake of illustration, I can also represent the flue gas CO2, H2O, N2 and O2. So, CO2 here is 0.075, 0.050, 0.47 and 0.025. Mind you, they are all in kg moles. Now, same flue gas will be out because the moles are not consumed, only heat exchange is there. So, CO2 which is exiting, that will also be equal to 0.075, H2O that is equal to 0.05, N2 that is equal to 0.47 and O2 that will be equal to 0.05. Mind you, they are all in kg moles. So, that is how the heat balance it rather appears. Now, what we do now, what we can do? We can calculate again the efficiency limit and so on. So, if I calculate now sensible heat in POC, so sensible heat in POC, the values already I have given. So, if I substitute all these values, then sensible heat in POC, it comes to be equal to 7073 kilocalorie. You have to simply multiply the heat content CO2, H2O, N2 and O2 at the respective temperature, and you will get the sensible heat in POC because temperature is same as it was earlier. So, now we have to calculate regenerator efficiency. Regenerator efficiency. So, first we will calculate efficiency limit. Efficiency limit, that will be equal to amount of heat at the flue gas temperature. So, that will be equal to 0.4136 into 10389 is the heat content in nitrogen plus 0.1099 into 11,000 divided by 7073. So, the efficiency limit is now 77.8%. We got this efficiency limit of 77.8%. So, now we can calculate overall thermal efficiency. Overall thermal efficiency, that will be efficiency limit into relative efficiency. So, multiply it, you will be getting 62.3%. So, what does it mean? Only 62.3% of the heat content of flue gas will be available in the form of preheating air. So, now if I make say heat balance of the regenerative zone, heat balance of the regenerative zone, then it will look, so again I have to do heat input and heat output. So, heat input, that is sensible heat in flue gas, sensible heat in flue gas, and that is equal to 7073 kilocalorie. So, heat output, sensible heat in air, that we could recover 4406 all in kilocalorie, sensible heat in flue gas, which is leaving the regenerator 1960, and we are assuming 10% losses of the sensible heat input to the regenerator. So, heat loss 10% of this, that is 707. So, total we will be getting again 7073 kilocalorie. So, now we can calculate the gross available heat to furnace, that will be equal to 10642, which was the calorific value of the fuel, because you are using the same amount of fuel with the same calorific value, plus 4406 is the heat added, minus 7073 is the heat taken out by the POC. So, gross available heat is 7975 kilocalorie. So, what we note from here, say with 125% air and 15% air leakage and 15% air leakage, now 75% of NCV of fuel is available. So, in this particular example, what we have done, we have used the same fuel, 90% carbon, 10% hydrogen of the same calorific value, that was 10642 as I given in just in the previous lecture. So, all that we have found out now, with 125% air and 15% air leakage, now 75% of NCV of fuel is available. So, I will wait for the analysis of the answer till I do one more case. Let us take it now case 4. Now, case 4 comprises of the 125% theoretical air, 15% air leakage, but the relative efficiency of the regenerator is now 60%. Now, since the amount of theoretical air is same as that of case 3, air leakage is also same as that of case 3, only relative efficiency has changed to 60%. So, as a result of the change in relative efficiency, overall efficiency will change and efficiency limit will remain same as that of earlier. So, now we can calculate, say, efficiency limit as we have just calculated. Efficiency limit we found 77.8%. So, we can find out overall thermal efficiency. Overall thermal efficiency, that will be equal to 46.68%. So, now if I do the heat balance, then heat input and heat output. So, you see now sensible heat in now heat balance of a regenerator. So, sensible heat in, that is equal to 7073 kilocalorie, sensible heat in air, output heat in air, that is equal to 3302 kilocalorie, sensible heat in flue gas leaving the regenerator, that is equal to now 3694 and heat loss are same. Heat loss are 707. So, total again is 7073. So, what you note from here in terms of percentage, we are able to recover only 46.68%, but 43.32% of the heat of the flue gas is lost, and of course, this is the 10% which we have assumed. So, now if we calculate gross available heat to the working chamber, you can calculate, this will come out to be 6872 kilocalorie. Now, only 65% of NCV would be available. Now, just as a further, if we calculate what will be the effect on fuel consumption. So, we can calculate now, say fuel consumption for 60% relative efficiency, that will be equal to, say, gross available heat requirement, as you know this formula, upon 6872 now the heat available, and fuel consumption for 80% relative efficiency, that will be equal to gross heat available requirement would be same, it is 7975. So, if you calculate the increase in fuel consumption, so you note that due to decrease in relative efficiency of the regenerator, it is obvious, since the gross available heat to the furnace has decreased. So, naturally the fuel consumption will increase. So, I can calculate from here now, say fuel consumption at 60% divide by fuel consumption at 80%, that will come out to be equal to 1.161. So, straight away extra 16.1% fuel will be consumed more than when relative efficiency is 80%. So, now you can understand the importance of a heat recovery device. A heat recovery device, if it is more efficient in terms of extracting the heat from the flue gases as well as transferring the heat to the incoming air, it will be more efficient. And as you see from here with this illustration, that higher relative efficiency, of course, lower will be fuel consumption, and lower relative efficiency will increase the fuel consumption, as you see. Now, if I summarize the contents of both the lectures, then the following result comes. So, if I do summary of calculations, it results, say what we have done, we have taken excess air, then air leakage, then gross available heat in kilocalorie, then relative efficiency, and then gross available heat upon NCV of fuel. That is what we have calculated. Now, we have taken 110% excess air, air leakage was first of all 0%, gross available heat was 8716, and relative efficiency we assumed 80%, and this figure we got 81.9%. Now, second case we have taken 110% of excess air, 15% air leakage, 8117 is the gross available heat. We assumed 80% relative efficiency and we got 76.2% of gross available heat could be recovered. Third case we have taken 125% excess air, 15% air leakage, gross available heat was 7975. We assumed again 80% is the relative efficiency and the heat available was 75% of the gross available heat of the net calorific value of fuel. The fourth case we have taken 125%, 15% air leakage, 6872, 60% and 65% over here. Instantly we can see from here that air leakage, it decreases the gross available heat. Also instantly you can see from here increase in excess air, which is now 120. If we compare now red with the green one, that is 110% and 15% air leakage, compare if it is 125% excess air and 15% air leakage, then there is a very slight difference in the amount of heat which is referred to the NCV of the fuel. It was 76.2% and 75%. So, the air leakage could be to some extent can be compensated by the use of excess air. Now, let us summarize this whole thing. So, what it leads to? For example, in the first case, say we calculate now, say we consider now fuel consumption. A, say in the above case, for example, if we take FC 0% air leakage, that will be equal to gross available heat required upon 8716 and FC 15% air leakage, that will be equal to gross available heat upon 8117. So, the increase in fuel consumption, that will be around 7%. So, this illustrates the effect of air leakage on the fuel consumption. Now, B, say use of excess air. Use of excess air with the same air leakage, 15% air leakage. So, now we calculate now, say for example, GAH 110% and 0% air leakage, that is was 8716 and GAH with 125% and 15% air leakage, that is equal to 7975. So, if we calculate now increased fuel consumption, now here due to excess air plus air leakage, that is equal to 9%. Now, if you compare case A with case B, in case A 15% excess air use was giving you only 7% increase in fuel consumption. Now, increase the excess air leakage I kept of the 15%, increase in fuel consumption is only 9%. It is obvious, because what I am doing now, the extra amount of air which I have put it is also being preheated in the regenerator. So, that is an important thing now. So, both these observations, now both the observations suggest, both observations suggest, number one, air leakage is detrimental to fuel economy. It is relative than excess air. As you have seen this calculation, therefore, furnace design should ensure minimum air leakage into the furnace. Now, that is a very important conclusion. Now, anywhere there are cracks in the refractory design or whatever the sources of leakage of air, that should be minimized to the extent possible, because this is much detrimental to the fuel consumption as compared with slightly amount of excess air. Now, therefore, slight overpressure within the furnace chamber is desired to avoid the leakage of air, but one should be careful that if the pressure inside the chamber is high, then the leakage of the products of combustion is very much possible. So, the furnace design and combustion chamber pressure must be optimized such that air leakage is minimum, and no leakage of products of combustion occurs. Mind you, the products of combustion, in many instances it contains CO also. It is highly hazardous, and if one is not careful, then it will pollute the environment. So, it is in this respect one should work, that is, the air leakage should be minimum and no leakage of POC occurs. Now, another thing that we have seen also, the effect of regenerator efficiency. So, what we have noted in the calculation, say decrease in regenerator efficiency